My name is Mitchell Falgoust. I'm a graduate student in Dr. Kroll's group, and I'll be presenting machine learning interatomic potentials for the conversion of polysiloxanes to SiO ceramics. As for an introduction, polysiloxanes are polymers that have an SiO backbone with organic substituents. They can be pyrolyzed to give SiO ceramics, which have a glass phase comprised of SiO and SiC bonds and usually have free carbon. And they exhibit a number of interesting properties. As for motivation, quantum chemical methods are accurate but computationally expensive, and we would like to run simulations on very large systems. So we suppose the novel class of machine learning interatomic potentials is a good way to apply DFT accuracy to large systems. We use moment tensor potentials to fit DFT energies, forces, and stresses to moment polynomials with a number of parameters that are designed or that are fit to reproduce DFT data. So for preliminary results, we do some low temperature VDOS or vibrational density of states, which parallels experimental IR, and we show that the vibrations in MLIP are nicely replicated when compared to DFT when using a couple of polymer examples such as polydimethyl and polydiphenyl siloxane. We also show a number of localized reactions involving methyl insertion between silicon and then methane formation. And then we run a large-scale 1 million atom simulation of PDPHS pyrolysis. We also do a cross-linking study to analyze the impact of cross-linking on thermal stability, and we also look at some degradation mechanisms for that, which involve the generation of these cyclic oligomers you see here. And then the next project is the genesis of free carbon, in which we look at the free carbon formation in PDMS, and we look at its growth and its extension and the impact of system size on the morphology. So as you can see from this middle picture here, for a small system we see one flake of free carbon, for a larger system we see a few, and then for a very large system we see far more. And for the initial genesis of free carbon, it's this step-by-step sequential growth in which you see incremental growth of the number of rings, and then the larger scale percolation in which two large sheets combine together to dramatically increase the extent of the sheets. As for future work, we're looking at improving the potential, as well as scaling up to models including 10 million atoms or larger. We also want to look at thermal conductivity as a function of free carbon, as well as a more in-depth study of gas formation using a slab model you see here. So to summarize, we developed the machine learning potential for the simulation of pyrolysis of polysiloxanes. We demonstrated some preliminary results, and then we looked at some more complicated things such as the impact of cross-linking on thermal stability, and then we also explored the mechanisms of free carbon formation and growth. And thank you.